Okay, I wanted to talk statistics with you guys about the midterm. The the average before I counted all the bonus points, I find that to be valuable. Thinking about how bonus points actually change the course of the exam. The average before bonus points was an 80%, an 80.8%. That's a B minus, which I would say is a pretty good average for an OCHEM 2 midterm. Here is the distribution of those points. I know online might not be able to see this. So I've color coordinated it. Blue is an A, green is a B, yellow is a C, D is orange, and anything below a D then is red. So the average was an 80. An average was an 80 before the bonus points were counted in. Maybe that's misleading because this is a bimodal distribution. There's a lot of A's, not a lot of B's, and then a lot of C's. So it's kind of misleading that the average is a B because most students didn't get a B, you know? After the bonus points, you can see, the numbers aren't always exactly what they seem, but yeah, pretty much only one person that had an A didn't go above 100%, stayed within an A. Only one person from the B's got up into an A, but then 3 of the C's jumped up into a B. And the average after bonus was an 86, almost a B plus. Again, most people didn't have a B plus, but at least that was literally in the middle this time. I find that this is actually very normal. The first time that I taught a class and I had this kind of bimodal distribution, I really thought that I had done something wrong in my class. I had set up my grading, I had set up my test questions, I had set up the way I taught in such a way that I was disproportionately favoring some students and not others or something. And then after talking with other faculty, it turns out this is fairly normal, and I think it's a result of the demographic that takes classes at the community college. We have some very motivated students that work incredibly hard, other students still motivated that maybe just don't have the time or effort to the time or energy to put in the same effort. I'm not sure. But this often happens, this bimodal distribution. And I'd like to say less than 30 people in our class, technically we don't meet the minimum for statistical analysis. So I plead the fifth or whatever. Any questions from the midterm? I will upload the key tomorrow if I can remember to. But I'm happy to look at any of these questions with you guys.
Can we go over the arrow pushing for how kind of failing is made?
You know what? We will actually learn the arrow pushing for that reaction as a part of Unit 4. Okay. The acid catalyzed esterification. But I can give you a little sneak peek of it. So I'm not going to make this as in-depth as it will be later on. We have the alcohol on the tertiary carbon and the carboxylic acid. I said this earlier. I was originally planning to make drawing the structure of phenolphthalein a required part of the synthesis. And then I decided not to. And I should have flipped this. I should have given you phenolphthalein that has the new ester and then just asked you to provide the reagents, because carboxylic acid and alcohol to form ester was one of our learning objectives, one of the reactions in the alcohols unit. I just didn't think of it. So I'm gonna abbreviate this. Actually, I'm just gonna show this as kind of a different structure, abbreviating all of it. In acidic conditions, we're going to talk a lot about acidic and basic conditions in Unit 4 and Unit 5. There's a lot of things that can happen, but there's really only one plausible route that gets us to making the ester, and that is something acts as a base to become protonated. We just mentioned in our class on Tuesday that carbonyls are both nucleophilic and electrophilic, and they're nucleophilic or basic from their oxygen. The oxygen of the carbonyl acts as a base. So this becomes protonated, which heightens the electrophilicity of the carbonyl carbon, makes it a better electrophile. And this is when we get the connection between the alcohol oxygen and the carbonyl carbon. You'll notice positive, positive, positive charge stays consistent throughout. This is the point where a base is necessary. A base abstracts this hydrogen. What is my conjugate base? What is the conjugate base of H+? Nothing. The conjugate base of H+ is nothing, right? So I don't have a conjugate base to send electrons to, so I actually just have electrons leave back to the oxygen, and I can't show anything coming to this, which is really awkward. And so here I have a diol and an ether all connected at the same position. And then the last couple of steps of this esterification, we protonate one of those alcohols and we kick it off as a leaving group so that we can reform a carbonyl. Yeah, we kick off a molecule of water. And here we could actually say water acts as the base to deprotonate in this last step. Okay, not every esterification is going to form a ring, but phenolphthalein does. And if you count the carbons, or the atoms rather, oxygen, 2, 3, 4, 5, that's the carbon of the carbonyl, so that's a 5-membered ring that it would form. It was certainly a challenging problem. There were some good guesses. Some people gave me like an aldehyde. Not sure how an acid will reduce carboxylic acid. Some people gave me a diol, which is actually also reduction of the carboxylic acid. There were other attempts. I think one person made a ring, but it was like to a carbon on one of the benzene rings, so it didn't quite work. Byproduct here actually would be H3O+. So that's your mechanism. This will be on the final exam, by the way, this mechanism. We're going to go through it more in the next coming weeks.
What was the final reagent?
The final reagent is H+. Does acid catalyzed hydration. Oh, oxidation. So either KMnO4 and heat, or CrO3 H2SO4, chromic acid, which oxidizes the methyl into the carboxylic acid, benzylic oxidation. I'm curious, was that too challenging, that template structure? Okay. Most people did pretty well on it. It made sense how to fill it in. You would have rather drawn it on your own? Yeah, right.
I didn't even know that I was supposed to go in. I just completely missed it.
So this was the wording, highlighted in bold, big letters template.
Yeah.
I really tried to give you as much of it as I could. And it was in boxes, right? Everything that you answered was in a box. So I apologize for that. I know that's kind of tricky. I would have hoped, though, that you'd look at that structure and say, how the hell does sodium hydroxide get rid of an alcohol and 2 bromines and give us hydrogens? But that was a challenge. Yeah.
You bold so many things.
Actually, I tried to bold the minimum of things, like to draw attention to what's important. Chiral, step 1, step 2. I should have bolded most reactive and EAS. And I bold the points so that the points stand out a little bit more. Take a stab. We have like 24 or maybe 23 students in class. Take a stab at how many students you think did EAS versus NAS mechanisms. 21 did EAS. What?
Everybody?
Everybody did EAS. What do you think is easier, an EAS mechanism or an NAS mechanism? It's your decision. I'm not here to tell you which one is easier. You think EAS?
But this was weird because of the typo.
Yeah.
So I did NAS because I was like, I don't want to be wrong.
And I apologize for that. I couldn't correct it in time. I only noticed it during the exam. Yeah. Yeah. It was all but 2, I think. I think 2 students gave me the NAS mechanism. And in my opinion, NAS, I told you guys this too when we started doing these mechanisms. I think NAS is easier because you don't have to activate the electrophile, so it saves you on steps. Remember I said that the 2 mechanism choices would have the same number of steps? Well, EAS had activating the electrophile, chlorine attacks the catalyst, and NAS doesn't have any of that activation, which means the NAS mechanism actually had an additional resonance form. We know that all aromatic substitution reactions have a minimum of 3 resonance forms. The chlorination had 4, and the NAS had 5 resonance forms. Kind of a lot, that's fair, but
That's why I decided
because there was too many resonance forms?
Well, I just looked at the NAS and I knew it was going to be more resonance forms based on what was added.
But it was the same number of steps.
I just didn't like that it was a strong point for me, so I picked the one that I figured would have less resonance forms.
Okay, sure. Less resonance forms, so maybe you can convince yourself the steps are right better.
Well, I saw the nitrogen and I was like, I don't want to deal with it.
Interesting. I know I made that mistake with the chlorination, so I was willing to accept some like deviations, like other mistakes in your mechanism. For instance, if you didn't realize that I had pointed that out and you had put a second chlorine on, I would have accepted it, and I guess I would have been okay with you deciding where to put it, although we know it would be directed ortho to the nitrogen. But instead I got some other weird structural errors, like people that were putting the chlorine in different positions than what was actually shown, even though they had fixed the error on their structure. And then one of the most common mistakes in the mechanism was activating the electrophile incorrectly. So not forming a chlorine aluminum bond, but just like separating the 2 chlorine atoms and having a Cl+. Or showing resonance forms and then attacking the electrophile, rather than attacking the electrophile and then having the resonance forms inside of the ring during the sigma complex. And then the other challenge for me was remembering how I had decided to break up the points. So you'll notice this was out of 6 points. It was 6 steps. I gave half a point per step, but then also a quarter point per step for the arrows, and a quarter point per step for the lone pairs and formal charges. But that meant that if if you missed a step, you didn't have the step or the arrows or the formal charges, which ended up just being 1 point per step lost. That was kind of the intention. So then the alternative there was like if you did other wrong steps, you'd still get partial credit for some of the work you showed in there, but would lose credit for having things that weren't correct. Some of you will notice that I kind of annotated structure in certain points, and I don't actually say structure up in here. So structure is kind of included in formal charges and the major resonance forms of the intermediate if you had your bond shown in the wrong spot. You guys asked me what was the most challenging question, what I thought was the most challenging question on the exam, and I will always say it is mechanisms and synthesis. In my opinion, synthesis is truly the hardest problem because I almost always make a new synthesis problem. I never show you one you've seen before. But mechanisms, on the other hand, I consider mechanisms to be fairly plug and chug. If you can get the steps down, you'll never have to guess. The only thing you have to work to understand on the mechanisms, especially here, is how many resonance forms should I expect and what atoms are involved in those resonance forms. So if I have any advice on improving your score for the mechanism going forward, it would be practice, practice, practice. Take the mechanisms we do in class and then try them again from memory and then compare to what you saw on the board, what you have in your notes, and see what mistakes you made and what things you got right, and then do it again. Come back and do it again. Come back and do it again. You can't really memorize a mechanism because they always change, but you can familiarize yourself with the steps of the mechanism. And then, of course, put examples on the cheat sheet. If you're going to use the cheat sheet, put your examples on there. All right, this is where I saw some really interesting ones. The right-hand side synthesis, reduction to the alcohol, followed by radical halogenation, gives you that benzylic bromine. And then the epoxide synthesis, which is basically the Williamson ether synthesis, NaH. And the oxygen deprotonates and kicks off the bromine to form the epoxide. I wasn't expecting that. One person gave me radical halogenation before reduction of the ketone, which actually works just as well, if not better. We'll actually see radical halogenation of the ketone, or of the, radical halogenation next to carbonyls later in the semester, Unit 5. I wasn't expecting radical halogenation in that synthesis. I was expecting reduction to an alcohol, dehydration to an alkene, and epoxidation. That's what I have on the key as well. But there is nothing wrong with the radical halogenation step. Reduction, dehydration, and then epoxidation. But what most people gave me was radical halogenation, because we've got the ring here. And then they gave me NaH to get to the epoxide. It worked. I had to think about it at first. Oh, somebody else. Oh, maybe this was the same one that did the radical halogenation first. I think just gave me reduction, LaH, and didn't give me an aqueous workup. You know what forms after reduction, right? You get the O-, which is what you need to make the epoxide. That's what you get with the NaH. So they went straight from there to the epoxide. Is that right? That's fewer steps, yeah? Was it just 2 steps? 1 intermediate? That would have been the most. That's shorter than my synthesis. My synthesis was 2 intermediates, 3 steps. That's why it was 5 points. I think some people gave me longer syntheses on some of these. I don't take off additional points so long as it all works and it's plausible. But if there are steps in there that don't really work, then you lose some of the points for that. By the way, I want to talk about this. Some people will give me abbreviations of their aromatic structure by putting like pH and then having more than one group attached to it. This came up. I think one person did it in the mechanism, but they abbreviated it before the ring was even used, so it didn't really matter. But more people gave it to me during the roadmap. In that big box coming down, where we do acyl addition, a lot of people gave me MEPHMGBr, which is not incorrect because the structure I was looking for was this, but it's missing information. MEPHMGBr doesn't tell me whether your groups are ortho, meta, or para to each other, and that structural isomerism is important to get the product that we have. So I think I took off half a point there for not having described the substitution of the ring more. For the most part, I was looking at 1 point for the Grignard, 1 point for the aqueous workup. I kind of hinted for you that there's an aqueous workup in that step by putting the 1, 2, but I still needed to see you put it in there because there are other things you can do 2 steps at once, and that's what I wanted you to see was, I'm going to do a Grignard, I need to do an aqueous workup with it. Typically, even if I don't put 1, 2, I still split the points between 1 point Grignard, 1 point aqueous workup. Similarly, when you had to do EAS bromination, I gave 1 point for BR2 and 1 point for the catalyst. Some people gave me BR2 with light, and they lost 1 point because they didn't have the catalyst that was needed. Some people, after the oxidation on the top, gave me something to this effect. Although a lot of them actually drew out their ring as well. 2 things wrong with this, yeah? Lost a carbon during that oxidation. The benzylic carbon is gone. And five bonds to carbon, breaks the octet. On that note, I was really excited for this bonus problem. Oh, and I have to apologize. I kept skipping this bonus problem while I was grading. So some of you have 2 grades in red, and one is crossed out and one is circled. That's because I forgot to grade your synthesis bonus points. So I had to go back and recalculate. I saw a number of people that took uracil and took electrons away from oxygen to give them to the nitrogen groups. 2 things wrong with that. Oxygen owns those electrons. Carbon can't take them to share with the nitrogen and breaks the octet of the nitrogens. They already have 8 electrons, so they can't accept any more. So the correct answer here was actually showing nitrogen sharing its lone pairs with the carbonyls that are in the ring to make that aromatic type structure, which gives us positive charges on the nitrogens and negatives on the oxygen. And so I was grading this as 1 point. Oh, this is what it was. 1 point for the structure, half a point for the explanation. And the explanation was, this is probably the major resonance form because it has minimum charges. The structure that seems to indicate aromatic nature has maximum charges. And we often draw our resonance forms with minimum charges. So if your explanation was something along the lines of charges, you got a quarter point or a half point for the explanation. And if your structure was going towards this, then you got some amount of the 1 point for the structure. But then I also took away some partial credit if you were missing the charges, if you didn't actually have your charges completely shown, stuff like that. No other questions on the midterm?
Actually, on that page 15, which had no reaction with the cuminaldehyde.
So chromic acid will oxidize the alkyl group. We're going to learn in this unit that the chromic acid will also oxidize the aldehyde. Hydrazine reduces the aldehyde to a methyl group. Sodium borohydride also reduces the aldehyde to an alcohol. So it's the anti-Markovnikov HBr addition, the HBr with H2O2. There's no alkene to react with here. So there's no reaction with HBr and H2O2. Killian, was that your question?
21A.
Okay, so you know what? Some of you brought up some interesting things in the bonus here in your rationale that I guess I didn't consider while I was building this. So you can see that they all have this negative charge floating around, but the nitro group has an additional positive and negative charge. That's the nature of the nitro group. You can't get away from it. So I didn't think of this positive and negative as being maximum charges, and some of you did. Some of you looked at D and said D has maximum charges. It's the most minor contributor, which I guess is actually my fault for not just having the molecule have all of these groups connected on the same structure. I should have probably just not swapped out that position, and I should have just made these all of these groups connected around the structure and then just shown different resonance forms. So I think that's my fault. We know that the nitro group is actually a strong electron withdrawing group. And these are all examples of NAS intermediates. So we should have said D promotes NAS the most, which means that D stabilizes this intermediate the most. So D is actually the major contributor, despite the fact that it does have maximum charges. One thing to notice there is that the negative charge ends up on the oxygen, where it never ends up on any of the other structures. Then having the negative charge on nitrogen is better than having it on carbon. So the two carbon structures were on the more minor side. The nitrogen better, and the oxygen the most major contributor. So then it's a debate between, is the negative more stable on carbon that is tertiary or carbon that is secondary? You should flip your carbocation trend. A positive on a tertiary carbocation is the most stable. So a negative on a tertiary carbon is the least stable. It has the most repulsion against it, the least stabilization. So secondary is more stable than tertiary for the carbanion.
Did you teach that in your Gen Chem 1 class?
Not in Gen Chem 1. I don't talk about positive charge or negative charge on carbon in Gen Chem 1.
Well,
You mean OChem 1?
no, Gen Chem 1. You can talk about anions and cations.
Not on carbons. I don't. Maybe you've heard of it, but I didn't.
Yeah.
Have you been to my Gen Chem class?
No, I just thought it was Gen Chem.
Yeah.
That's an OChem thing?
Yeah, I would say, I mean, seeing as how organic chemistry is all about the carbons, you talk about a lot of other types of ions in general chemistry, usually polyatomic ions and metal ions, or I guess non-metal ions, but not carbon. Carbon usually doesn't form an ion until you get into Gen Chem or OChem like this. Okay. In my announcement where I talked about the statistics, I also addressed that you now have a midterm analysis assignment due. And I want to talk to you a little bit about the analysis assignment so that we're all on the same page. You guys, I think you realize at this point that I do not hand out credit. I don't give points. You have to earn them. And this assignment is one that you have to work towards. Some of you may have submitted an assignment like this in my OChem 1 class, and you may have not received all of the points that you were expecting, and that's because if you don't actually answer everything correctly, or if you don't provide everything I'm looking for, I don't give all of the points. So you have to earn these points. You can earn up to half of the points that you lost, which means there are 2 students in our class that can't even turn in this assignment because they didn't lose any points. That means you can't earn back bonus points. Those were points you didn't lose. Yeah? Those are points you just didn't get. So you can earn up to half the points you lost. I would say that this assignment is made far more for those students on the bottom half of the class grade distribution. I told you guys already that those who score well typically get most of the bonus points. You can even see that in the distribution. Almost everybody that had an A got bonus points that brought them above an A. But nobody with a D or failing, and few of the people with C's, half the people with C's, didn't get enough bonus points to change their grade. So this is made for the people on the bottom half of the grade distribution because you earn more points back the more points you lose. 3 things that I want from each answer that you got wrong. Provide and explain the correct answer. I'm going to upload the key so you don't have to guess at what the right answer is, but you can't just say what the right answer is. I want you to explain it. Something here like, my answer was wrong because I didn't take into account blah, blah, blah. Or the correct answer is right because when you consider these factors, blah, blah, blah. I want this short. I want it concise, so keep it under 2 sentences. Why did this appear on the exam? My previous students used to have to kind of guess at this, and they would say something along the lines of, because we talked about it in class. Yeah, usually when we talk about it in class, it does go on the exam. But you all have access to these learning objectives documents under each module, which means you can actually come back and say, well, in section 17, under learning objectives 3, we saw that NaS with aryl halides and sodium hydroxide was a learning objective. That was something we were supposed to learn in this class. That's why this question was on here. The third part is a reflection. What kept you from getting this right? I have a lot of students that will just copy and paste the same thing. I just didn't study. I just got confused. I just didn't know it. They don't really give me any depth. And maybe that's all it is. Maybe you just didn't study. What I don't want is for you to be harsh on yourself. I don't want you to say things that tear you down or remove your belief in yourself to improve going forward. The whole point of this assignment is to master the concepts that you missed. The reflection part is identifying why you missed them in the first point. So don't be harsh and say, I'm just not good at this and I'm never going to get it. But see if you can actually identify. This was a section I didn't have good notes on. This was a section I didn't go back to enough to review. this was a section I never understood, and maybe here's what I'll do different going forward. In terms of formatting, it really helps me if you take each question individually and answer these 3 things about them. So if you have like a Word document and you just have a picture of the first question and then those 3 things about it. Picture of the next question and those 3 things about it. Some people give me pictures of the entire exam, and then after all of that, they have the 3 things for each question. And I have to do a lot of scrolling back and forth to kind of see how many points did you lose, what did you actually get wrong, what is your explanation saying. So it helps me if I can have kind of the question and the answers all together. Some of you do this like on your tablets too, and that's kind of the same deal. Like just take a screenshot or whatever and then just annotate next to it. Last thing I have to say, mechanisms. I would encourage you to rewrite the mechanism. I'm not sure that I'm actually going to accept just my like a screenshot of my key mechanism as the correct answer for the mechanism problems. But remember, it's explaining why you got it wrong and not just showing me the correct mechanism. I don't care that you found my key and the mechanism on it. I'd rather see that you can copy it down again and show it correctly. But you also have to explain why your answer was wrong or explain why it's correct. So there's going to be some descriptive passage for the mechanism as well. So what I would encourage you with the mechanisms is identify what I wrote and why I took points off, or what I circled to indicate what you got wrong, and then say something like, I drew a 5-bonded carbon, LOL. I forgot to show my charge. Whoops. I have only one of the 2 arrows needed for this step. So you have to kind of identify what you did wrong in that mechanism. And I try to give you that helping hand by circling things and annotating a little bit. Questions?
Actually, that's not a question.
Yes.
I kind of want to do this with the bonus questions.
You can do it for the bonus questions. You will not earn points back for the bonus questions. And I may or may not respond to it.
Okay.
Yeah? Like I may just actually go through and just give you feedback on yes or like what points you earned back for the actual questions. But yeah, do it for the bonus questions and say, do the reflection, do the explanation. I think every professor, well, not every professor allows you to have your exams back. I think professors that give you your exams back would expect you to review it. I used to return my exams, and I totally expected students to go through and figure out what they got wrong so that they could improve on that for the cumulative final. But they don't. So this is my way of incentivizing it. Not only should you be mastering this better to prepare for the final, but you'll also change your midterm grade. You know, the sad thing is I don't see maybe half the class turn these in. Certainly not the half of the class that needs to do it. Probably half of the students that really could benefit are the ones that turn it in. The half of the students that could benefit from it don't turn it in. And then I get students that missed like 6 points, turn it in, and they get their 3 points back. Great. That didn't change the course of their semester. It didn't change the course of their grade. But they did it anyways because they see the value in it. So model that example and do it. Do it over a while. You don't have to do it right now. You don't have to do it next week. This is due December 11th, but I will accept it all the way until December 17th at 11:50 p.m. 5:50 p.m. Do you know what is at December 17th at 11:50? 5:50 p.m. Our final exam starts 5:50 p.m. Why would I not accept this after the final exam? There is no point. Oh, it's not the 17th, sorry. It's the 16th. There's no point. The whole value in this exercise is to prepare you to do better on the final. Remember that I have a final grade replacement. So if your score on the final is higher than your course grade, you take the final exam score as your course grade. That's a safety net, so that if something came up that kept you from really doing well all semester, you can prove you mastered all of the semester's concepts on the final exam. I'm happy to allow that. If I didn't give a final, I wouldn't allow it. Or sorry, if I didn't give a cumulative final, I wouldn't allow it. So it's due December 16th, right before we start the final.
Just on that note, I guess, with the makeup points, is it from the, how much for like the bonus points applied, or is it from the original?
Yeah, from the original. So your grade in blue is what you actually got on the exam before bonus points. I grade in blue for the psychology of it. You guys have heard that, like, when you are graded in red, it negatively affects you psychologically. So I grade in blue so that you don't feel offended by the things you got wrong. And then I try to give you reverse psychology, and I give you bonus points in red. So when you look at the red grade and it's higher than your blue grade, you're like, damn, I did so bad, but it's better than I did in blue, right? I'm trying to right the wrong that has been done over centuries to the color red. That's intentional. So your blue grade is what you can actually earn back. Actually, I say this in here too. You may earn up to half the points you lost. If your midterm grade is above 100% with the bonus points, the assignment is still for you. Yeah? Like you could have lost 5 points on the exam, and then you earned all 7 of the extra credit points, so your grade is actually over 100. You can still turn it in, and you can make your grade more than 100. Truth be told, students that have over 100 on the midterm typically score an A on the final and an A in the class. So I guess I'm not worried about giving 2.5 extra points to the midterm grade for that student, you know? So blue grade is what you can earn back. Okay. All right. Switching gears. Let's look back at this worksheet that we were doing in class on Tuesday. I apologize for not having more copies brought with me today. But let's do some of this nomenclature. So remember that you got a question?
Was this up on campus?
It is.
What was it under?
At the top of Module 4. And I think it's called Carbonyls. Should I be able to see that? Yep, just Carbonyls. Remember that a compound's name has a prefix, which, you know, for a lot of compounds, especially in OChem 1, the prefix is like most of the name. A prefix, a root, sometimes a locant, and a suffix. And here we're actually seeing how a lot of these carbonyl groups give us some sort of suffix stopper, where we identify the hydrocarbon chain that gives us the suffix, and then we look at the major functional group that gives us the suffix stopper. I don't want to ask how many of you already did these names, and I kind of don't want to ask at the same time. Let's talk about this first one together. What's the parent chain? Pro, 3 carbons. What's the suffix? Yeah, the aldehyde will actually be the suffix stopper. You guys should see. I don't know if anybody else talks about suffix stopper. I don't know. I can't remember if I made that up or not. Propene, suffix stopper, al, for the aldehyde. So the root suffix and suffix stopper is propenal. Do I need locants? Do I need a locant for where the aldehyde is? The aldehyde is always position 1. You never have to give a locant for the aldehyde. Do I need a locant for where the alkene is? It's nice.
And I like it.
Yeah,
I think
it's
for this specific structure, then I have to make sure that aldehyde and the benzene are
there's no other choice.
tell us where it is.
There's actually no choice on where the alkene could be, except that it's on carbon 2. So we don't really need the locant for the alkene, but it's not wrong to add it in here. And then how do I describe the benzene ring? Phenyl, and numbered by where the aldehyde is. It's coming off of the 3rd carbon in the chain. True that it could be coming off of the 2nd carbon in the chain. Yeah. So 3-phenyl. I know somebody said benzyl, but benzyl, remember, is the CH2 coming off of benzene. This is just the benzene. 3-phenyl propene now. Could I add anything to this name to improve it? Yeah, I could. I could make it 3-phenyl prop 2-ene al, or 3-phenyl 2-propenal. But there's something else I could add that would improve the description of this structure.
Cis?
Yeah, actually E, not cis. Trans or E. Yep. You know, that brings up an interesting thing from the midterm. I had a few people that put P4-isopropyl benzaldehyde. And I wasn't sure how to grade that because you're kind of saying the same thing twice. So I think I took a small number of points off for saying the same thing twice. I was looking for P or for 4. All right, what about my second one? Oh, Cooper.
Just remind me what the E is again.
Yeah, E and Z describe the
Oh,
structure of the alkene.
Okay.
Yep. So there could be a Z alkene.
And then it would be
More like zig-zig.
okay.
Hexadone.
Hexadone is a terrible name for that. What?
D is for carbonyl, like amide.
Okay, sorry. Cyclohexanone. Hexadone? I think I'm still confused, Gilly.
Was hexadone there?
Why do you have a D in that name at all? Hexadone? No, we were talking about amide and amine.
No, I just thought D was a good way to differentiate carbonyl.
No. So the parent chain is cyclohexane, and the suffix based on that ketone is -one. So E gets dropped from ane, and you get cyclohexanone. Kind of a nice name in my opinion, and it's a nice molecule.
I work with that molecule.
You what?
I work with that.
For what purpose?
Bonding agent.
It's a bonding agent in like adhesives.
Like, it's like it's in plastics. So like a bunch of like valves or like lures and stuff, they get bonded on like tubing. That's what we use.
It's a liquid in a bottle, and then you put it in. It must dissolve the plastics a little bit.
Yeah.
And then it basically welds the plastics to each other.
Mhm.
Wow, that's very interesting.
Cool.
Absolutely. Now you know it.
Yeah.
Well, you already knew it.
I already know it, but now I know what it looks like.
Now you know what it looks like. All right. What about this last structure? Raise of hands. Functional group present here. Cooper. Acid anhydride. You can also just call it an anhydride. Why do we call it acid anhydride? Yeah. Don't like all carbonyls look a little like a carboxylic acid? So anhydride tells us without water, less water. Yeah? Acid, less water. What happens if you less water from acid, carboxylic acid? Well, actually nothing. But if you have two equivalences of carboxylic acid and you less water, then you can fuse them together. So there's an equivalence of water that's missing that would give you two carboxylic acids. So what would we name this? Propanoic anhydride. 3-carbon chain, propane. Oic is the same suffix that carboxylic acids get, but instead of oic acid, we get oic anhydride. Anybody want to debate why I don't need to say dipropanoic anhydride? If it's right in the middle, then couldn't I just say di? Yeah. So by being an anhydride, we know there are two carbonyl carbon chain groups. So I guess like the anhydride already implies two equivalences of carbonyl groups. And so if I'm saying propanoic anhydride, I know they're both propanoic. And how do we describe it if it's asymmetric? We would just give both roots with oic at the end, like propanoic benzoic anhydride we looked at yesterday, or the other class. Benzoic anhydride would be, if you had just benzoic anhydride, yeah, you'd have something like this. If you had acetic benzoic anhydride, you'd have something like this. By the way, we're going to talk about common names today too.
You have methanoic anhydride?
Yes, but you would call it, you might call it formoic anhydride. We can look it up actually. Okay, I actually wanted to do one more. This is in the second row on the far right. Formic anhydride. I don't know why I said formoic. You see it, Killian? That's your formic anhydride. Methanoic anhydride would be systematic. We're going to talk about that systematic nomenclature. What would you give this? oxo. Is it a ketone?
We're not referring to the
Aldehyde's named here at al. Actually, you're not spacing. Yeah, that's a good point. L, M, and O, P. It is alphabetical. Thank you. Butanol. No, sorry. Butanol. 3-oxo doesn't mean ketone. It can also mean aldehyde. Is that fair? We looked at an example at the end of last class, right? Where we had dioxo, 3,5-dioxopentanoic acid, because that actually gave us a ketone and an aldehyde being described by oxo. What's higher priority, alcohol or ketone? Ketone. So that doesn't just mean that ketone ends up in the suffix as the suffix stopper. It also means that you prioritize numbering so that the ketone has the lowest login.
So, let's say you had one, I don't know, oh my gosh, man, totally spaced my question. Okay, I'll ask when I remember it.
Okay. I wanted to talk about the functional class. Oops, that's not how you spell it. Force of habit spelling functional group with FG. Sometimes you'll hear ketones named with their functional class nomenclature. Functional class is when you say isopropyl alcohol instead of isopropanol, or really 2,2-propanol, propane 2-ol. Propane 2-ol is fully systematic. Isopropanol is like a little bit common, isopropyl, with systematic suffix ol. But isopropyl alcohol names the alkyl group as a substituent of the alcohol group. There's a common organic solvent that has been phased out over the last year and a half by the EPA, or it's been heavily regulated, so we've phased it out of our labs, called dichloromethane. But dichloromethane is also commonly referred to as methylene chloride. Methylene is what we call a CH2 group. And so if I have methylene chloride, then it must be bonded to 2 other halogens. But you can also have methyl chloride, methyl iodide. Those are all functional class. Ketones have their functional class nomenclature, where we name the 2 sides of it. So this compound we call acetone. We can also call it 2-propanone. Acetone is common. 2-propanone is systematic. Its functional class is dimethyl ketone. How many carbons are indicated in the name 2-propanone? 3 carbons, prop. How many carbons are indicated in the name dimethyl ketone? Dimethyl. But we know there's 3. So then the last carbon must be in the ketone. You can't have a ketone without a carbon. So you can count, I know I always kind of forget to say this, but in nomenclature, you can count the number of carbons in the name. Dimethyl is 2, ketone is the 3rd. here's a ketone we'll use in Unit 5 quite a bit. Can you give the functional class name for this and the systematic name for this? Tert-butyl is one of those groups. Tert-butyl methyl ketone.
Is it called functional class of ketones because we're assuming the ketone's the biggest functional group, the most important one we want?
I'm just looking at the functional class nomenclature of ketones. I'm just not looking at any of the other functional groups. I gave examples, the functional class nomenclature of alcohols, methyl alcohol instead of methanol. Functional class nomenclature of alkyl halides, methyl iodide, benzyl bromide. That's functional class nomenclature of alkyl halides. This is functional class nomenclature of ketones. You can do others. I'm just focusing on this one. Systematic name? You got it, Jacob?
2-oxo-3,3-dimethylbutane.
Systematic will still use the suffix stopper for the ketone. Yeah. So rather than naming the ketone as a substituent, we're going to identify that as the primary functional group. You want to try again? Okay.
Once I think about that.
3,3-dimethylbutane.
Right. So there's two answers I would accept here. 3,3-dimethylbutanone. You cannot have a butanone where the ketone is not on the second carbon. If the ketone is on the first carbon, that's a butanal. If the ketone is on the third carbon, you numbered the wrong direction. So you can clarify this by calling it 3,3-dimethyl-2-butanone, or 3,3-dimethyl-butan-2-one. But this is totally an acceptable name. In fact, the version that doesn't have the methyls, there are a lot of people that call this 2-butanone. Like I said, there is no 3-butanone, there is no 1-butanone, so it's a little silly to call it 2-butanone. But I think it's one of those things where it rolls off the tongue, and so people just get used to saying it.
So if we have, say, longer carbon chain than most ones we've seen, there was 2 ketones, would we just be putting like 2,3 or 2,4 own and to clarify the second ketone? Or
yeah.
is it going to go into the, if you know what I'm saying?
Yeah, this is a good question. I don't know the answer off the top of my head, whether you get that suffix. You know how you get diol, triol, tetrol. So why don't we just do a little search to see how it classifies it. My instinct is to name one of them as oxo and the other as ketone, but no, you had the right instinct. You get dione, 2,4-pentane dione, 2,3-hexane dione. Actually, notice something about the suffix stopper. The E comes back. You drop the E only when you are following N by a vowel. But if it's not going to be followed by a vowel, you bring the E back. I don't think I give you any of those. All right. The other thing I wanted to talk about with nomenclature was actually common names. The 1-carbon carbonyl. Ah, the functional. No. No, I wouldn't ask you to know the functional class of that diketone. At a certain point, functional class kind of gets less useful. I have a feeling the functional class of that molecule would be called acetone methyl ketone, because they're going to look at this and they're going to say, well, this is an acetone group. Yeah. The 1-carbon carbonyl. That's an example. If I have a 1-carbon carbonyl with an aldehyde, then I have formaldehyde. You're all familiar with formaldehyde, yeah? How many of you have ever worked with formaldehyde? A few? Stinky?
Well, I was just in the cadaver lab, so.
Yeah, love it, hate it. Good. What else? Why does it have to be an aldehyde? Formate. Formate, we need an alkyl group at the start. You want to pick one? Methyl? So we could write it as a line, you could write it as a bond to CH3, you could write it as OCH3. That's an ester. We know it's an ester because of the suffix ate. That suffix O8 or 8 is what's given to esters. So we need an alkyl in the prefix. Methyl formate. Have you ever worked with this? What made you think of it? Steroids. So steroids have formate in them?
I'm sure there's one. Acetate is one.
Well, acetate we'll get to, yeah. A 1-carbon carbonyl, correct? So 1-carbon carbonyl doesn't need to just be the aldehyde. It's also the ester. What else? Formic acid. Have you ever worked with that?
No, but
It's in ant bites. Thank you, James. You couldn't have set me up better for that. Formic comes from the Greek, the acid produced by ants. I mean, literally ant acid, but not like the ant acid that you take to cure reflux. Ants acid.
What are they called? Forms? Look, line of forms.
I don't know. But it comes from the Greek. It has no meaning. It's not systematic. This form suffix, or this form root, it literally just comes from Greek for ant acid. This is why you don't want to get bit by ants, I guess, especially in Greece, or you'll get formic acid. Formic acid is nasty, too. I think that if you ever produce formic acid in your body, bad things happen. Oh, this is why you don't want to drink methanol. Not funny. Methanol will oxidize into formaldehyde, and if formaldehyde oxidizes, it becomes formic acid. Methanol, by the way, highly toxic. Like, ethanol is a poison. Methanol is highly toxic. Did you guys have I told you guys the story of the undergraduates that had an underage party, I think in Arizona? Somebody must have worked for a chemistry lab, and they said, I'll bring alcohol to spike the punch with, and grabbed methanol, spiked the punch, and killed like dozens to hundreds of college students at this party. They all died of methanol poisoning. There's an episode of House where somebody comes in with methanol poisoning, and you know how you treat methanol poisoning? Swear to God. You overdose them on ethanol. Yeah. Because you are having a metabolic competition between metabolizing ethanol and metabolizing methanol. It's very similar to how you treat carbon monoxide poisoning. You guys know how to treat carbon monoxide poisoning? Dioxide? You give it pure oxygen.
The thing is, I've had too many patients in these actual scenarios. I've had a patient who drank methanol, and I've had multiple patients with carbon monoxide.
Scary. Carbon monoxide binds to the iron in your hemoglobin, which famously carries oxygen to your blood. So carbon monoxide poisoning, suffocates you from the inside out, suffocates you intracellularly. So how do you combat that? You have to overcompete with extra oxygen. You just pump oxygen into them. It is kind of an equilibrium thing, yeah. And it's a similar process with overcompeting ethanol and methanol. Obviously, taking ethanol is not a prescription unless you are overdosed, like you have methanol poisoning. All right, here's another one. What would we call this? Acid won't be in it.
Form of chloride?
Yes.
No way.
Formoyl chloride.
Oh, why oil?
Well, because that's what the acid chloride gets. The acid chloride gets the suffix oil chloride.
What's chloroform?
Chloroform, actually we'll learn the chloroform reaction in Unit 5. Chloroform is CHCl3, and we're going to learn that we can produce this via the haloform reaction. So you can also make bromoform, you can make iodoform. Chloroform is just this. But I guess that's, I don't know actually if the form there is related to this form, but it's still a one carbon group. It's not a one carbon carbonyl, but it is a one carbon group. We can look into that to see if those forms are related.
Does that say TUE as in Tuesday or something? Oh.
Sorry, my cursive is not perfect. All right, what's the last one we could look at? What do we call this? Not formamine, formamide. It's that D versus N that changes between an amide and an amine. This is formamide. On your sheet, you have a compound, a very common organic solvent, although not one that we actually use in our labs. So now I want you guys to name this. Yep. We have to describe that both of those methyls are coming off of the nitrogen and not somewhere else in the carbon chain. There isn't anywhere else in the carbon chain they could come from. But that's the systematic way. N,N-dimethyl formamide. Again, because there's nowhere else that those methyls could be coming off of, it is pretty common to hear this called dimethyl formamide, but actually it's most often just referred to as DMF. Has anybody worked with DMF before? That's okay. I forgive you. DMF is it's a cool solvent. I think it's cool because of its structure, to be honest.
So the CH2Cl2 is toxic to the environment and a really good solvent, but the other one's chloroform. We'll add one more chlorine to chloroform. Yeah.
Yep. And chloroform is also a good solvent for organic chemistry. I know we're not using the NMR that's in the OChem lab right now, but once we get to use it more, deuterated chloroform is one of the most common organic solvents for NMR. CDCl3. But deuterated solvents, they readily exchange hydrogens with water in the atmosphere. So no matter what, when you run a solvent with CDCl3, you inevitably get a signal from the CHCl3 that has exchanged its proton with the atmosphere. Okay, Another one is the 2-carbon carbonyl. Now, this is where I'm sure all of you can think of some really common examples. So let's see if we can go around the room and no one give more than just one example. Who wants to go first? Acetonitrile. CH3CN. Good. Maddie. Acetone. You know, some places you'll see acetone written like this. But we know the structure of acetone.
Do you know why acetone after you spray it on your hand makes that white stuff?
It's drying your skin.
That's skin?
Pretty sure, yeah.
White stuff?
What's else? What else?
Acetic acid.
Acetic acid.
This is a reach, but acetaminophen.
Actually, let's take a look, shall we? Well, let's see. How do you pronounce that?
Oh.
Yeah, I was making a reference. Do you see a 2-carbon carbonyl in there? It's an acetamide group. Specifically, N-paraphenyl acetamide, or N-parahydroxybenzyl, or N-parahydroxyphenyl acetamide. Mm-hmm. Absolutely. Acetaminophen, yeah. The only thing you don't get from acetaminophen in the name is that there's a phenol group. You don't get the hydroxy group. I think some people would argue amino is in there, acet, amino, then, but it's not an amino group. An amino group is an amine. This is an amide group. So let's use that as our example. I'm going to actually name it, but if you wanted to put Tylenol next to it, you could. This is N-parahydroxyphenyl acetamide. Oh, I forgot my H. It's not. Willow bark has salicylic acid. Acetyl salicylic acid. Let's look at what acetyl salicylic acid looks like. It's got that 2-carbon carbonyl, but this time it's an ester. So if you know salicylic acid has a carboxylic acid and an OH group. Based on our section 15 nomenclature, aromatic ring nomenclature, we could also, sorry, did I say that wrong? This is an alcohol in salicylic acid. We could call it parahydroxybenzoic acid or 2-hydroxybenzoic acid. So when we say acetyl salicylic acid, it's not really describing that it's an ester, but that's really the only thing it could be. You're taking the hydroxy group and you're acylating it. You're turning it into an acetyl group. Okay, what other compounds can you think of? Acetyl chloride. This one is functional class nomenclature. No, it's not. No, I guess it's still systematic. But we're not using the OYL. Good. Cooper.
How exactly is the acetone 2-carbonyl has 3 carbons?
Well, it's an acetone. So it's a ketone that is like a 2-carbon carbonyl from either direction. That's how I would interpret it. But I'm not a big fan of common names in the first place, so other people might have a different reason why they think that's right. Anything else? Acetate. Acetate, an ester, so we need an alkyl prefix. For instance, ethyl acetate. Who's worked with ethyl acetate before? You probably have in the OChem lab. Any others? There's one more. Acetaldehyde. Yeah? All right, here's the deal. I forgot to give you guys a break. So if you need a break, feel free to take that. We're going to take 5. And otherwise, if you're not going to take a break, work on that sheet and see what other compounds you can name and what compounds are more challenging to you.
Why did I should have just. Why did I know that? She made it. Yeah. I know she got stabbed 4 times. She was stabbed for her, like, on the road. She's 60. I'm like, how do you stab her?
Not really.
Well, 60. And then she was, you know, she was like,
I mean, there has to be movement, right?
no, I do not. I'll look at the call.
Doesn't mean it's actually created. Oh, yeah, it's so stuffy.
It's not as
Yeah,
hard
this
as it was
feels
the
like
first
I
time.
know.
You were all extra.
You were all working really hard, and there were a lot of people.
Smoke coming out of the ear.
She must have had staff back then.
Okay,
That
that's
is not a mess.
for an hour now because I'm like so confused. You only have 2 hands, like how are you holding your?
What is that?
Oh, it's just you stabbed me.
I thought
That's acetate.
I'm so confused.
Maybe
Yeah.
she fell, maybe
That's
she fell
ethyl.
right though, where she fell, where she was naturally applying pressure.
So why don't we just write it
I don't know,
down?
the body's pretty amazing.
Why didn't we put
I'm
acetate?
trying to see.
Acetate's not a functional group so much as it's the conjugate base of the carboxylic acid.
Oh, okay, so if it was the
I
base.
don't see them like this.
Yes, propanoate. Or propioate. Common name. Propioate.
Was there a common group?
No, I think just the propio. Like they put IO in there for some reason. Ah, okay. No. Because acetyl chloride has to have like the CH3 group. I would actually call this cyclopropyl formoyl chloride. Yeah, Killian?
What's the name of the top long man who wears camo?
Smart one. Jacob?
Hey, John. No,
Jamie.
fake
Talk
blood.
about Jamie.
Oh,
Yeah,
he wears camo?
long fingers.
Oh, pff.
Jamie?
I made a mistake. It's not formoyl.
Oh, really?
I don't know what you, I have nothing.
Hear me out. Formal chloride.
I think formal. I was saying formal the other day, and formal chloride makes the most sense in my opinion. But I just wasn't saying it that way. Okay, what about him?
Oh, I bet he got 100. You can't tell me legally.
I can't legally. I cannot.
Not legally. Because you just have to wait till you retire. Or till he comes
Or
back.
or you can ask him.
I'm gonna ask.
Canvas Messenger allows you to actually message him directly.
I also think
Now you know his name though. I don't think he would have come up on Canvas Messenger as tall blonde guy that wears camo. Does he really wear camo?
I don't really think so. I know how
At least twice.
Killian talks. I can decipher it.
at least twice.
At least twice. Okay. I guess I just haven't noticed it.
It makes sense that you haven't noticed it.
It's camo. It's camouflage. Wow. Good one. No, tell me.
So, there, in the handouts that you had in the last few things, they have all this word, and I keep trying to get them to go across, and they just won't translate. Could you just make a PDF version, even if it's bad?
This one's a PDF.
This one is, but not like, I had a list in my computer that.
The learning objectives.
Learning objectives.
Mhm.
The last handout I had to do Jewish level for I'll send you like an email with all of them.
Please.
Because I had my computer, and it was different.
Shoot. Oh. Yeah. Yeah. Send me a list. I'll update it tomorrow. Yeah. Yes, I can do that. I'll tell you what, the reason these are all PDFs and not Word documents, I make these images on my Mac and then I just paste them into Word. And if I upload that Word doc from my PC, it gets blurry. So I save it as a PDF. But the learning objectives I don't save as PDFs because they look fine. But
I'll send you like a whole next list. But that's why you don't know where else to use it. And then you actually see them. You're like, that's one.
sounds good. Any compounds on here that you were having a hard time naming?
Number 3-1. 3-1.
Yeah, I would have a hard time naming this too. Oh, I did want to transition us back in and say these are common names. So I will never require you to show me a common name. You guys noticed, though, on the midterm that there were some questions that had common names in them? Like it was, which of the following is the product of bromination of compound 1? And then it was orthobromotoluene, metabromotoluene, parabromotoluene, yeah? So you had to know that compound 1 must be toluene. It's getting brominated. So I want you to be familiar with common names. I'm never going to require that you give me a common name, which means all of these compounds can be named systematically as well. So how would you name our 1-carbon carbonyls? Formaldehyde. What's a better name? That's systematic. What's the length of the parent chain? Meth. And what's the suffix? Al. So this is methanal. What about methylformate? Prefix methyl. Parent chain's root is meth. Methanoate. Formic acid. Not methoic, because you still need a suffix, and then you'll stopper it with oic acid. Is there an alkene? Is there an alkyne? No. So then you get the ane, and you stopper ane with oic acid, methanoic acid. Right? This is like saying, I have methanal, or methane, but it's an aldehyde. Methanal. Methanoic acid. Formal chloride, becomes methanoyl chloride. Formamide becomes methanamide. Did you notice we didn't have a nitrile for the 1-carbon carbonyl? Because that would just be cyanide. Right? Because the carbon of the nitrile would be the 1-carbon. And if that's bonded to something, that's hydrogen cyanide, which is a gas, or cyanide if it was deprotonated. So we wouldn't ever call it form nitrile, just cyanide. Okay, what about this last one? Well, I guess dimethyl, NN-dimethyl methanamide. What about the 2-carbon carbonyls? What would be the systematic name of acetonitrile? What's the root? F. And the suffix, ane, een, or ein? Or een, ein? Een. No, not een. Ane. There's no alkene, there's no alkyne. So, ethane nitrile. Remember, the nitrile is weird in that the E comes back. Acetone, well, we actually already talked about this one. Propanone or 2-propanone. This is the weird one because it's not just a 2-carbon carbonyl, but there's another methyl group on the other side. But by acetone, we're saying, inferring that it's an acid on both sides ketone. It's a ketone of 2 acids. Don't know, I didn't make up the common names. What would you call acetic acid? Ethanoic acid. What would you call acetaminophen if you didn't have any of the common names in it? You'd still start with this N-p-hydroxyphenyl, phenyl. What's the longest carbon chain that contains the highest priority functional group? Ethane. And the functional group is the amide, which gives the suffix stopper, amide. So we get ethanamide. I mean, what do you guys think? You like the common name or you like the systematic better? Some of you are all looking really confused at the systematic name. It's a 2-carbon chain. Ethane.
Does that bottom name account for the carbonyl somewhere?
No. No, it's this. Oh, this bottom name?
The red, the long one.
Ethanamide.
Yeah. Where does it account for the carbonyl? That's the whole.
Well, actually, we would number it the other way. That's ethanamide. It's a 2-carbon amide.
Oh, I see.
If this wasn't on here, that's ethanamide.
Got it. Okay, I see where I missed it.
But it's actually just a substituted ethanamide. Okay. What about acetyl chloride? Ethanoyl. Ethyl acetate. Ethyl doesn't change. Come on, you're getting into the swing of it. So remember, common names often change the suffix that we get. Like we have oic acid, O8, oil chloride, but then we actually just get ic acid, O chloride, 8. It's like we drop the O that comes with a lot of these suffixes. In systematic names, those O's come back. So ethyl, ethanoate. Acetaldehyde.
Where's the 8? Why is it not?
The ester group gets suffixed O8. Acetaldehyde. Ethanal. Okay, there were a couple I actually wanted. We skipped one functional group in both the 1-carbon and the 2-carbon carbonyls. Formic anhydride. Common systematic name. Methanoic anhydride. 2-carbon carbonyl anhydride.
Does that react with water?
Sure, all anhydrides do. Acetic anhydride. Same name as the acid, but drop acid and recognize that it's an anhydride. Common name, ethanoic anhydride. Okay, just to reiterate what I mentioned before, our systematic suffixes, they often have these O's in them, oic acid. In the common names, those O's sometimes are dropped. Methanoic acid, formic instead of formoic acid. Formol chloride, methanoyl chloride. I suspect it's something to do with the linguistics of how it sounds. So, some of you wanted to name this compound. What's the longest carbon chain containing the principal functional group? One carbon chain. So you could either choose formyl chloride or methanoyl chloride. What's the substituent coming off of it? Cyclopropyl. It's a cyclopropyl substituent off of a one-carbon carbonyl. So cyclopropyl, formyl chloride, or cyclopropyl, methanoyl chloride. What else? What other compounds on this list confused you? Oh, this one? Now this actually changes a little bit because when you're attached to the aromatic ring, you can call it some sort of benz carbonyl. Benzoic acid, benzaldehyde, benzoyl chloride. I suppose I did the one carbon carbonyl, I did the two carbon carbonyl. I should have done the benzene carbonyl common names. Benzaldehyde, benzoic acid, benzoic anhydride, benzoyl chloride, benzamide. So this would actually be benzoate because it's an ester. Methyl benzoate. What about the one to the right of it? Good. Phenylethanoate or phenylacetate. What about the one just below phenylacetate? Nice. No. Okay, yeah, sorry. You nailed it. But instead of naming the cyano as a substituent, name it in the suffix.
Do you want us to name the 2-methyl instead?
Yes. 2-methyl what? Butane nitrile. Nitriles get the suffix nitrile. It's a nitrile. It's a CN. You nailed it. It's a cyano group, a nitrile. 2-methyl butane nitrile.
But if you put the carbon in the chain, then what do you care about what the nitrogen's bonded to instead?
You know it's bonded to CN.
But 2 H's. So me?
There's not 2 H's on the nitrogen. There's never been 2 H's on a CN group. Yeah. Cyanide. So here we're counting the first carbon as the nitrile, and we're naming carbon 2 then has a methyl group coming off of it. That one I suspected would be a little bit trippy, especially because of the way it's oriented. It's oriented almost as if the nitrile is a substituent.
I know we're doing more like a common name setup, but do you have a preference between those 2?
No. I think if a multiple choice question was there that said, which of the following is not an acceptable name, and then like 2-cyanobutane, 2-methylbutane nitrile, and then like you could also call it sec-butyl cyanide, or maybe sec-butyl nitrile. That would possibly also be accurate. Those are a little bit more challenging because it has to be a name that has like three or four different ways you can look at it. So I want you to be familiar enough with it, but you'd never have to come up with it on your own. If that makes sense? All right. Taking you guys way past time. Thank you for your time. You should be able to start on sections 19, 20, and 21 active, just looking for nomenclature. We're going to dive deep into reactions next week. Have a good weekend.